Swayam Prabha. Digital India. Educated India.
Welcome. We are discussing the topics in the course High Performance Computing for Scientists and Engineers, and today we'll start the second module of the course, which is OpenMP programming, and this lecture and the subsequent lectures will discuss on Introduction to OpenMP. Before this, we had 2 weeks lectures in our first module, which was Fundamentals of Parallel Computing. In the first module, we have discussed about architectures of parallel computing systems. We have discussed about shared memory and distributed memory parallel computing systems, and we also discussed about appropriate algorithms for parallelizing a job for both of these systems, and then we have also discussed about performance metrics of the parallel systems. So this have given us a background to start working on actual parallel programming, and there are 2 broadly different systems of parallel computing. One is distributed memory system, another is shared memory system. We have discussed these things in detail in our previous lectures. In the distributed memory systems, there are a number of computers which have their own local memory space, and a large job is broken down into multiple smaller jobs. Each will have their own local memory space, and each of the computers will update the data and do the processing in that local memory space, and they will in between interact within each other using message passing algorithm. In the shared memory, it is much simpler than distributed memory computing, both program wise as well as architecture wise. We'll also discuss it in a while, but there is a common global address space in which multiple processors are connected, and they try to update data at different locations at the same time instant, or they work parallel to update data of the different locations of the same memory space. Well, the third one will discuss about GPUs or graphics processing units at the end of our course, but right now we'll first focus on shared memory parallel computing and writing programs on that using a API called OpenMP. This is actually much simpler than CUDA based GPU programming or MPI based distributed memory programming. Also, most of us are probably having a computer, a PC, or a workstation which has multiple processors. So when we go to buy computers, we go for dual core, quad core processors. Therefore, a computer which we already have has multiple processing units or multiple CPUs connected with a common memory space. So if we learn OpenMP very easily, we can get our hands dirty in parallel programming using OpenMP, because the computers which we are having in our home or in our office, which is readily available to us without doing any further hardware augmentation, like using a GPU card or using a network cable, we can use it for doing OpenMP programming. So let's start with the first lecture of the module 2, and this is 12th lecture in our course, which is Introduction to OpenMP. And in this lecture and in subsequent lectures, we will discuss about thread parallelism, compilation and execution of OpenMP program, OpenMP programming model. I will show you some simple OpenMP sample programs, and you can take it from here and start developing your own OpenMP program, and OpenMP data handling using shared and private variables and different nuances of that. Again, when we talk about OpenMP programming, we are trying to write a parallel program, and what we are trying to do here, that we go to a shared memory system where there is a common memory which is attached with multiple CPUs, and this can be done in different ways, and each of the CPU will look into different memory, different locations of the memory, but it's the same memory space, and each CPU is free to look into any of the memory locations, but through the program we'll see that each of the CPU will look into different locations of the memory and try to do their arithmetic and logical operations on these locations, and therefore if there are multiple operations, they can be done actually in parallel instead of running a do loop over them. Precisely that's what we are trying to do using OpenMP. As this course is about high performance computing for scientists and engineers, most of the domain people who work in some areas of science or engineering, or even some people from economics or business, we can consider this group also very much into using high performance computing for their own domain problems. These people many times have some legacy codes, or many times they have some algorithms which they can very easily convert into a program and run their problem. Now, in case they use some technique like OpenMP, it helps them in that sense that they can use multiple processors of the computers they are accessing day in and out, and use full utility of that computer where there are multiple processors of all the processors. Also, when we use some of the commercial software or some of the community developed software like OpenFOAM, like NAMD, there are a number of GROMACS, number of community developed software. These software also have some optimization within them, so that if you build them correctly for a multi CPU system, they have their own OpenMP constructs in between them, which you probably cannot see directly, but it's inside the source code of the software, which launches the job in multiple CPUs, and you get a actual parallel computation using that software. So, as an user also, domain experts may sometimes need to know what is happening within the source code, and or if they have to change something in the source code. In many cases these are open source codes. So, if you have a if you find that there is some incredible way of getting better performance in the code, or there is some new physics which you can explore using software whose source code is available to you, you will jump into the source code and try to update it. And then it also becomes important for the person to know OpenMP, because for many of these operations inside the program, OpenMP constructs are called. And for people from computer science background who are supposed to develop the source codes, these source codes are finally developed through computer science people, it's extremely essential if they are working in the domain of scientific computing, that they have to work with parallel codes, and especially OpenMP type of parallel codes in most of the cases. So, it is very important that we learn OpenMP properly, and this is also the first step in this course to learn how to write parallel programs, or this will be the first step for many of us while developing their own parallel program. Once you know some constructs of OpenMP, you will feel the joy of asking multiple processors of a computer to work in parallel. When you run a simple program, or when you write a simple code and compile it and execute it, you see that only one processor is active on that. But when you learn OpenMP, you can see yourself that you are asking multiple computers or multiple CPUs of the computer to run the job and crunch numbers for you and give output to you. So this is also important, and as I said, writing OpenMP programs, executing OpenMP programs doesn't require very high-end computing systems like a data center or something with a GPU card or at least a HPC cluster or rack with multiple servers connected via MIDI-NET switch. It doesn't require that. It is your simple desktop or laptop computers with multiple processors which you can use to do OpenMP programming. Then there can be another use when you are trying to do something, say you are trying to do a post processing of some data you got through your scientific computing program. When you are trying to do something, you can also use OpenMP to do it fast in a faster way, so that we are using multiple computers looking into different computers are looking into different files and giving you data, but they are looking from the same data space, same global address space. And we will see that typically single instruction multiple data program, and in some cases multiple instruction multiple data program we can do using OpenMP. So let's go into the business. We can see that if there are multiple CPUs connected with the common memory space, we can write OpenMP type of program which is for shared memory parallel programs in that. And what is good here, that there is a common data space, so all the computers are basically connecting accessing say if you have a variable A, if you have an array A, all the computers are accessing different locations of the array. You really do not need to make different copies of A, map them into some separate local memory, and then you have to track where which part of the memory should go and then combine them. You really need to do that, which you have to do for distributed memory systems. So there is less communication across the CPUs because everybody knows that they are connected to a common memory space and they are updating the data assigned by them. Who has assigned it? The programmer has assigned that which data which CPU will do, and that is precisely what we will do through OpenMP. You will see it. Another thing is important here, because it's the same variable A, it's the same array A whose different elements are being accessed by say different CPUs. We need a lot of synchronization in between them. So OpenMP, or I'll say shared memory programming, requires more synchronization but less communication, and also programming wise it is probably much simpler than distributed memory programs. So in a shared memory architecture, different processors are connected with a common address space. For symmetric multiprocessor, what is symmetric multiprocessors? There is a single space chunk of physically single or connected chunk of memory, and all the CPUs are connected with that chunk of memory, and we also call it uniform memory access, or UMA. This architecture we have discussed in our first few classes, in our first week's class. So it can be a symmetric multiprocessor where they are using physically the same memory location, or it also can be the other one is it also can be multi-processor arrangements where non-uniform memory access is given. That means different computers are connected with different pieces of memory. However, these memories are some way mapped to a global address space. And now when you connect the same memory with different processors, it might be a symmetric multiprocessor that are physically the same memory is connected with different processors. It can be a non-uniform memory access multiprocessor where different computers with independent memories are connected via an interconnect switch, and all these independent memories are mapped to a global address space. In this case, concurrent instructions can run in different processors while using the same memory, as I have shown here, that there is a same variable A, and different parts of this variable, different elements of this variable are being updated by different processors. At the same instance they can go, so therefore there are concurrent instructions which can be processed by different processors in parallel. Cache coherent protocols are required. This is very important. We have discussed about cache coherency in detail earlier, that if some part of A is updated, by CPU 1 and CPU 1 has some cache, all the processors has some cache, and this variable also is called by CPU 2. So, CPU, if the update which has been made on this variable by CPU 1 must be reflected in the cache of CPU 2. We have discussed about cache coherency earlier also, that whenever because it is a shared common global address space, whenever one processor updates something there, this must be reflected in all other processors cache, and that there are protocols for doing cache coherency which can lead to false sharing, which can lead to some sequential operation across the processors, etc., and it can degrade the performance. So because cache coherency has to be established, we have to be careful while dealing with the data in the shared memory system. Again, whatever I am discussing here is not specific for OpenMP, but it is general for all shared memory programming paradigm. Synchronizations across processors are important at different stages of the program, because it is the same memory which all the processors are trying to update, and it must be synchronized. Otherwise, some part of the memory may not be updated, and the processor starts working on something else, and there can be something wrong because the variable is, or the array is not completely updated. And in symmetric multiprocessing systems, shared memory parallel computers which are non-uniform NUMA, symmetric multiprocessing is uniform memory access UMA, and shared memory parallel computers are non-uniform memory access or NUMA systems, and GPUs also, they provide system support for execution of multiple independent instruction streams. So, they are connected to a same memory space, either physically or virtually. The memories are mapped to a common address space. Now, there also is a requirement of the system level support by the operating system, support by the other hardware, support by the scheduler of the processors which is inbuilt within the computer in the motherboard. This system level support is important so that all these computers can in parallel execute independent instruction streams, or concurrent operation of the processors on the same data space is possible, that is done through system level support, and symmetric multiprocessors and shared memory parallel computers as well as GPU cards, they provide this system support. So it is not only just the hardware, but using the software, the operating system, the scheduler inside the motherboard, everything needs to give a support for execution of parallel programs. And now each processor is executing their instruction stream on its own, and there are multiple processors and each are executing independent instruction streams. And these instruction streams which use data stream from common address space are known as threads. So, the instruction streams that is being operated by the processors, but they are taking data from a common address space, these instruction streams are known as threads, and threads are the units of parallelism here. So, when we will write parallel program in a shared memory system, we will mostly use this thread parallelism paradigm, and we will launch threads for concurrent operations at any instant. Threads run as part of main program using single instruction multiple data architecture. So, essentially a same instruction operated over different parts of the same data set, say SIMD, that is how the threads will work. But also multiple instruction multiple data, that means instruction streams, they are only concurrent and independent, but they are different instruction streams depending on the data they are working on. That is, it is also possible to use MIMD model in thread parallelism. Although the threads may run independently in different processors, they are often needed to perform synchronizations. True, I mean, if say if there is one variable all the processors are trying to update, they cannot do it. There is some synchronization required for them, and cache coherency is also required. If one is updating it and another is trying to read it, it requires cache coherency. So because all the threads, though they are running independently, they are pointing to same memory space, it's important to have synchronization in between them. It's also important to have cache coherency. So we can think something like this, that there is a train compartment where there are 8 berths and there are 8 passengers who will go to each of their independent berths. So this process can be done very well in parallel. Whoever has boarded train, you know that it's not that one has to wait for the other to take his own berth. However, some synchronization is needed, otherwise there will be contention, there will be race in between them. Somebody will probably obstruct others to go into his own place, thing like that, because it's the same area, it's the same memory location whose different elements are being accessed. It requires some synchronization, and also it is possible that some memory location will be accessed by multiple threads, and therefore some sort of what else, sequentiality will be required there. So these are different type of synchronizations, and also cache coherency protocols are required. We have discussed about cache coherency in much detail. We will also discuss some of the aspects later. Thread based parallelization is an alternative of message passing based program. In message passing, what happens that this is typically a distributed memory system programming, that each processor is connected with its own local memory space. So when one processor tries to update something, it updates only in its local memory space, and at particular instances when the programmer thinks that these updates are to be informed to some other processor, it passes a message or passes some data through network cable to that other processor, and the programmer has to control it, that when the data passing will be done, who will pass data to whom. But in thread parallelism, programmer really cannot control it. He has some control, but the entire thing he cannot control it, because it goes on the hardware and operating system of the system, that it's the same memory and different processors are writing to and reading from the same memory. So it is less on the programmer, more on the system, that how this the memory will be accessed by different processors. Well, we can see a small example here. Row matrix is multiplied by another matrix, and we are getting product as a row matrix. So how is this multiplication coming? That this row is being multiplied with this row. So each element, a row of this element is multiplied by first row of this column. Second column of this row is multiplied by second row of this column. Third column of the row is being multiplied by third row of the column, and this is summed up, and 1 into 7 7, 2 into 9 18, 7 plus 9 18 25 plus 33 58. This comes as 58. The second one is, this is multiplied with 8, this is multiplied with 2, and this is multiplied with 3, and the product comes here. So there are two columns who are independently, there are two columns who can be independently multiplied with the row, and their results will come here. So we can launch two threads. First thread will multiply this row with the first column, and this will be the output, and the second thread will do for the second column. So these two elements can be obtained in parallel if we run two threads in two different processors. So this is an example of a thread parallelism, that these two are obtained basically operating over two columns of the input data of one of the input data, and these operations can be done independently. So we will see some of the features of the threaded parallelism. One is portability. Threaded applications can be developed in serial platforms and run on parallel machines without any change. In case the number of threads are more than the number of available processors, they may be executed sequentially through a do loop. So we write an OpenMP program with the threads as discussed. Now when we will try to run it in a single processor architecture, we have a computer which has only one processor, but we launched 10 threads. So these 10 threads, they are 10 independent instruction sets. They actually will be operated simply as a do loop. 1 to 10, each of the threads will be operated. So if we have a computer system which has whose number of processors are less than the number of threads, what is the number of threads that we can control? That we can control through several ways. We can, within the program also, we can run that this part there will be this number of threads. Say we wrote that this, like earlier we saw 2 threads, there is a matrix with 8 columns, so there will be 8 threads there. Now we try to run it in a single processor computer. These 8 threads will be sequentially run using a do loop, and the advantage is that when writing a threaded program, you really do not need to bother about how many processors are available there. You can write the threaded program the way you want to parallelize that particular part of the program. Parallelize in the sense that the way you want to get the number of concurrent instructions for that particular instance of the program. And once you run it into a CPU which has less number of processors, a group of threads goes to each CPU, and this group of threads run as a do loop in the CPU, but all the CPUs execute these groups, like each of their groups, in parallel. So there is some parallelism in between them. If there are 4 CPUs and you launched 8 threads, each CPU will run 2 threads, but at one instant 4 of the CPUs have launched 4 threads. So you are getting 4 times speed in some sense. Speed will not be exactly 4x times because of overheads, but you are getting that here. So it is a portable threaded parallelization is a portable system of parallelization that you can take it to any computer system and run it. If the processors are less than the number of threads specified there will be some sequentiality and it will run. The next is latency hiding. In case multiple threads are operational on the same processor, then each thread introduces some latency. There are some part due to, say, memory access, IO, communicating, establishing cache coherency, etc. So each thread has introduced some latency, but while this thread is taking time for this latency, say this thread is trying to write something to the file system, there is some latency there. At the same instance, the next thread in the group of the threads given to the processor will be launched. So the latency of one thread will be hidden by operation of the next thread. So in some sense, this latencies, if we have threads much more than the number of threads much more than the number of processors, some part of the latency will be hidden, because when one thread will go to the latent state or take its overhead time, the other thread in the same group will be launched at the time on that processor. Scheduling and load balancing, because we understand, because we have developed the granularity, we have launched a number of we have found a number of concurrent instruction streams, finite number of concurrent instruction streams, which should be running at that instance of the program. It is very easy to distribute it among finite number of computers. So load balancing becomes easy because it's finite number of threads to be distributed across finite number of processors, and scheduling also becomes easy. We will see about some of the schedulers which OpenMP provides later. And ease of programming. It is easy to identify the region of which the main program has high concurrency. It's something like a do loop where each of the operations are independent in the do loop. The next operation does not have to wait for the previous operations result. So, they are independent instruction streams. Instead of do loop, you write threads, you launch threads there, and therefore programmer can identify the region where it can be parallelized, there are high concurrency, and specify threads using simple APIs like pthreads, OpenMP, etc. there to run. Well, so we have introduced some backgrounds on I have given you some backgrounds on shared memory parallel programming, and we came to the idea of thread parallelization. We'll see one more little more details on this, and then we'll conclude this session. That if we look into the other, there is another advantage of thread parallelism. If we look into program, certain program, there are some sequential component in it. Say we can consider this case. Say I have a set of n numbers, and I have to find out the max of them, maximum of n numbers. So I make some groups, say p groups, each has n by p numbers, p groups, and ask n by p threads to find out the max for each of these. And then all these local maxes are collected somewhere, and I find out the global max. So instead of doing this over n numbers, I am doing each thread is operating over n by p numbers, and if each thread is going to a independent processor, it is operating faster, it is using the parallelism. Now this can be done in parallel in 4 processors, but this part is a sequential part, because output from all the processors will come and only one processor will run it. So we cannot ask launch 4 threads here. If we have launched p threads here, we cannot launch p threads at this location. This part is inherently sequential, and we have seen that any program has certain sequential component in it. We remember Amdahl's law when we found out what is the highest possible efficiency of a parallel program. We have seen that there is a sequential part which will be limiting part on the efficiency of the algorithm. So we have to be able to control the number of threads. There will be a large number of threads. When we will go to the sequential part, the threads, most of the threads will be destroyed, only one thread will be active, will take care of the sequential part. Again, when another part of parallelism will come, these threads will be active, and this is done through creation and destruction of the threads using a fork join model. And we can see that if we have a parallel program which is running, the main program is running in this direction, in x direction, the serial part only one thread is active. When the parallel part comes, the thread parallelism forks it into multiple threads, and different threads take care of different parts of different groups of the instruction stream, the main program. So different instruction streams are launched, and when we have to again go to the serial part, all these threads join and one thread remains active, and we go to the serial part. So this is another very important feature of thread parallelism, and we should keep in mind that it is not that all threads are active throughout the parallel program. At different instance we can launch number of threads will be active, and in the sequential regime only one thread is active. So I will conclude the introduction to OpenMP's first lecture here, and will in the next few lectures we will look about the programming model of OpenMP, how to compile and run OpenMP jobs, and very importantly we will also look about how different type of data handling is done in OpenMP, how to access shared memory variables in OpenMP, and in case some of the variables are very locally to be updated by the threads, what should we do for that. Okay, thanks.